So welcome back to the lecture, and the last two lectures, the theories that we had understood about generalized eigenspaces and generalized vectors leads to this particular lecture where we will actually go through the steps in order to see how we are able to transform a given matrix to the Jordan form while finding out the modal matrix. So that is our intention, and the problems would also come in that regard. So let us understand how this would happen. Now here you can see that in this so I have tried to break down the problem once, the theories that we have covered. So it leads to the problem is basically to find out given a matrix A. So given a matrix A, we have to find out the Jordan form and the modal matrix M, which is the matrix of all the generalized eigenvectors. Now to do this, so this is the way that the problem will be asked to you. So you will be given a matrix A, you will be asked to find out the J and M. Okay. How you have to go about it? So from the given matrix A, you can find these informations. This set of information you can readily find, which is the eigenvalues, the algebraic multiplicity of each eigenvalue, and the geometric multiplicity of each eigenvalue. This you can easily find out from the given matrix A. So you will also see that when we do the examples, we will also find this information first. So this is the first set of information that we need to find out. With the help of this, in many cases we would be able to figure out J. In many cases, but not all cases. That's why this dotted arrow is there. So not every time we will be able to figure out what J is, but most of the times our problem will be such that we will be able to figure out what J is with the information of the geometric multiplicity and algebraic multiplicity. But sometimes we will be not be able to figure out, uh, and then we have to go in this direction, and we actually have to always go in this direction of finding out the generalized eigenvectors. And when we find out the generalized eigenvectors, then we will automatically know what J is and what M is. M will give M, the set of generalized eigenvectors will give me M. We don't have to do M inverse AM to find out J. With the information of the generalized eigenvectors, actually we will also find out the information about the minimal polynomial. And when the minimal polynomial is found out, that is we know what is the size of the largest block of the corresponding eigenvalue, then with along this information of mg lambda and the minimal polynomial, we will be able to know what is my J by looking at the set of eigenvalues. The eigenvectors will give me that information basically. So when we find out this eigenvector, finding out is the actually the task. So how to go about finding out the eigenvectors? So there are two algorithms actually. The algo 1 starts with the vector v1 in the space omega 1. This is the initial eigenspace, a minus null space of a minus lambda I. That space is w1. So v1 we find out in w1, and subsequently we find out all the other higher order eigenvectors, higher order generalized eigenvectors. So this higher order, lower order, you may not find in any text or reference. This is what I am trying to term them in that way, so that it is easier for all of us to understand what we are trying to say. So I hope you understand what I mean by lower order eigenvectors and higher order eigenvectors. So they are basically the generalized eigenvectors which we eventually find out in the generalized eigenspaces, which are having the a minus lambda I raised to the power of 2 or 3 or 4, like that. null spaces of those matrices. So this is the algo 1, and what is the algo 2? Algo 2 is we start with the highest order eigenvector possible. So we go till wk, which is null space of a minus lambda I to the power of k, k being the index of the minimal polynomial for that corresponding eigenvalue. So if the eigenvalue is lambda, then x minus lambda will have an index of k in the minimal polynomial. We start with that space, null space of a minus lambda I to the power of k. That space we start from, and we start from an eigenvector in that space, and eventually find out the lower eigenvector. Which one is easier, which one is not, that is a question which actually depends on the exact A also, and how you are doing it in that manner also. Neither of this is too difficult. Only one has a certain type of steps to be followed, another has another type of steps to be followed. Normally it is seen that it might be your experience that algo 1 would be simpler to do, because you don't actually need to find out a minus lambda I square, cube, and other higher orders. But here you have to actually go till a minus lambda I to the power of k and start from there. However, matrix multiplications are not so difficult also. Once you understand how they are actually done, it's not very difficult. So that computation, additional computation is there in algo 2. However, as you can see here, as I have written, this algo 2 works for all types of transformations. So transformations from A matrix from A to J, this transformation will algo 2 will be able to work for all types of transformations. All types of transformations means what I mean by this. You will find that when you are doing this transformation, either there will be, for a particular eigenvalue which is repeated, for that particular eigenvalue, either there will be equal size of Jordan blocks, or there will be unequal size of Jordan blocks. Either these two possibilities are there. That means suppose eigenvalue is 2. That is the first example also that we will look into. You will see the eigenvalue is 2. The total the algebraic multiplicity is 4. The geometric multiplicity is 2. So from this information you are not sure what is the size of the largest block, because it can be 2-2 combination or 3-1 combination. So sizes can be 2 plus 2 or 3 plus 1, right? So but you will see also that the your minimal polynomial has x minus 2 square. So that definitely fixes the size of the size of the largest Jordan block, which is 2. That means the Jordan blocks are of equal size here, because total 4 and divided into 2 and 2. So the Jordan blocks are of size 2, equal size. In that case, we can go through algorithm 1 as well as algorithm 2. But in case suppose it was like 3 and 1, then it would be unequal size, and in unequal size we have to actually go through algorithm 2. So though algorithm 1 may seem easier, algorithm 2 is the more important one which we should understand, and we would go through both these algorithms, and you are allowed to use either of it when you have equal size of Jordan blocks. But if you have unequal size, you have to go through the route of algorithm 2. Now let us again just quickly have a revision of the theory. What we had in the theory is that we had this set of eigenvectors. These are the generalized eigenvectors which satisfy these relationships which are shown here. The set of generalized eigenvectors v1, v2, etc. up to vk satisfy these relationships. So they are eigenvectors of the corresponding null spaces of these matrices. So ai like vk minus 1 is the eigenvector of null space of a minus lambda I to the power of k minus 1. And also another relationship between these eigenvectors we have found out, which is vi minus 1 is a minus lambda I of vi. So if you know the higher order eigenvector, you will be able to find out the lower order eigenvector by simply doing a minus lambda I. That is the thing. There is another thing that I did not mention here. So this is that your vi is vi belongs to wi minus wi minus 1, and this is for all the i's. Okay, that means your vk belongs to this space omega k, but not in any of the lower eigenspaces. Similarly, v2 belongs to this null space of a minus lambda I square, but not in null space of a minus lambda I. That we should remember. Okay, this we need to remember when we are actually going through the algorithm 2, because there this becomes very important. We have to satisfy this condition and choose the vk. You will see when we go through the examples. So let us start with the examples. There are actually I think 4 examples that I wish to show. So let's see how long this takes, and I will try to go fast because now you know column operations, you know matrix multiplication. So these things I will try to go through fast. I will not explain the steps so much. What you have to note down is what are the actual steps I am performing. So you should also perform these steps one by one in order to solve a particular problem. So let us take the first matrix A. This is a 4 cross 4 matrix like this. And of course, the problem is to find out J and M. Okay. So here the first thing that you should find out is the lambda. So you figure out what the lambda would be. You will see that the lambda is only 2. I hope by now you are able to understand how to figure out lambda from a given matrix. This is by inspection you can find out this lambda actually. And if you are not able to find out by inspection, you have to go through the normal routine of finding out the lambda. Now ma lambda is obviously 4 here, that also you can see. Now what is your, we have to find out mg lambda, that is the case. So when we have to find out mg lambda, we have to have a minus 2i with us. This matrix we have to first find out. This is actually the 0th step. So a minus 2i, when you do, you will get this matrix. This is a very simple example actually, just to start ourselves to understand the steps. So this is a minus 2i. Now to find out mg lambda, we need to find out what? We need to find out the dimension of n a minus lambda I 2i, and it is very clear this is a minus 2i. So what is the dimension of the null space? The number of dependent columns. And for that, to find out number of dependent columns, usually you have to go through the column operation, but here you can very easily see that 2 columns are already 0 and the other 2 columns are clearly independent from each other. That means the dimension is 2. The dimension is 2. Now you are confused, what is the size of the largest Jordan block? We don't know yet, right? We don't know that yet. But if you have to actually figure that out, then you have to see what is the minimal polynomial. What is the minimal polynomial? So obviously the characteristic polynomial is Pax is x minus 2 to the power of 4. What is the minimal polynomial? We have to go on doing a minus 2i square cube etc and figure out. So let's do a minus 2i square, and you would be readily seeing that if you do this a minus 2i square, I will write it here, you will see that this is coming out to be 0. This means your max is x minus 2 square. From here you are getting the size of the largest block as 2, and hence there are only 2 Jordan blocks, each of size 2. However, this information, figuring this out, is not so important. While you go through the steps, this information will already be found out. So you can keep this information aside, you may not include this also in the steps. So let's first see, after we have done, even this information is not required. These are additional information which we calculated right now, not required actually. So what we did, from A we found out lambda, ma lambda, and then a minus lambda I. So lambda, there may be, then this is here, there is only one lambda. In another example we will have 2 different lambdas. So here there is only one lambda, we do the a minus lambda I. So a minus lambda we do, and then we figure out the dimension by looking at this. Even figuring out the dimension, this will automatically come. This is also not required to be found separately. So what are the actually things that we have done till now? We have to have this information, we have to have this information, we have to have this information. From here actually we would be able to figure out the eigenvectors. Actually we have to find out. So the next step is to find out the eigenvectors of a minus 2i of a minus 2i. That means the basis vector spanning the null space of a minus 2i. For this you have to do the column operations and see which are the basis vectors. Here you can immediately see from here by looking at this matrix, that my question is, what is that vector when multiplied with that this matrix gives me 0, right? So you see that the first column is the second column and the fourth column are already 0. So if in that vector, so I am writing like this, a minus 2i is span, I will directly write and then explain you. This is span of basically this vector and this vector. Why? Because you see that if I put a non-zero element in the second a non-zero entry in the second element of this vector, which multiplied to this matrix gives me 0, then I will get a 0 obviously. If I put a non-zero element in the first or the third, I will never get a 0, because the first element multiplies the first column, second element multiplies the second column, third element multiplies the third column, fourth element multiplies the fourth column. So now you can see that in order to obtain a result of 0, your first element and the third element needs to be 0. So first element and third element in both these are 0. Second and fourth element could be non-zero. Second and fourth element could be non-zero, and these two I separated out. These two I separated out. I did not put them into one single vector because that single vector could be separated into these two separate vectors. So these two are the spans. These two are the bases actually. Okay. So even if you had tried to do the column operation, what you would have done, you would have written these columns, and below you would have made the identity matrix, right? And now you see that already the top two columns are 0, so you look at the bottom two columns. For this, the bottom column is this. For this, the bottom column is this. So those columns have come out. So the column operation will always work. Please remember this. But sometimes, like in these cases, you don't have to actually go through constructing the table, because it is directly seen from the matrix what are the corresponding vectors which we want. So the null space of a minus 2i is found out. This actually gives me the dimension. We know that dimension is 2. So we don't need to find this out separately. So this gives me the dimension. So now we are in a confusion. What is the actually what is actually what is the how should I say that yeah, what is the size of the Jordan block? That is one question that is remaining. But you understand that at least two Jordan blocks are there. So two Jordan blocks are there. So either the combination would be 2 plus 2 or 3 plus 1. So if I go, so I have to actually go and find out a minus 2i square eventually. So eventually I have to find out a minus 2i square, and that is the reason why I actually go and figure out what a minus 2i square is. And if I do the a minus 2i square, I will see that I am getting a 0. This I have to do. Either I will get a non-zero or I will get a 0. Okay, in this case I have got a 0. So this clearly shows me that my my Jordan blocks are of equal sizes. So when they are of equal sizes, I can apply algorithm 1. Algorithm 1 applying means I now assign this to v11 and v12. Okay, the v1 means first one means the lowermost order eigenvector, and there are two numbers, one is with the another suffix 1, another is with another suffix 2. So these are the lowest order eigenvectors v11 and v12. There will be two lowest order eigenvectors with which we have to start and get the higher order eigenvector. And what is the relationship between the lower order eigenvectors and higher order eigenvectors? A minus 2i, a minus lambda I, v a minus lambda I v2 is equals to v1. I hope I am correct. Yeah, a minus lambda I v2 equals to v1. So this is the relationship. So now you have to find out what is that v21. For that you will get v11, and what is that v22. For that you will get v12. So this is what you should solve. So your a minus 2i is already, I am writing it down again, a minus 2i. So a minus 2i is 0 0 0 0 0 0 1 0 0 0 0 0 1 0 0. What is this? A B C D. This is your v21, which will give you v11, which is 0 1 0 0. This is your question. So from here you can readily see that this is the column which is getting reflected again here, right? This is a column which is getting reflected again here. So which one of these A B C D should be should you choose, like you can readily understand that A should be 0, B can be basically anything, but since it can be anything, we can choose it to be 0 also. C needs to be 1 because this has to be replicated. C needs to be 1, and all the others you can keep them 0 basically. So V21 is found out. V21 is 0, 0, 1. This is V21. Similarly, if you place here same exercise, you do 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and A, B, C, D. So this is your V22 equals to V12 is this, and you see, notice that this is getting reflected here. That means your A must be non-zero. So your V22 comes out to be 1, and others you can keep them 0. This is your V22, right? So let me just check with my note that we are doing it correctly. So 0, 1, 0, 0, then V12, V11 for this. V2 I got this, right, and this I got this, yeah. So this is correct. Okay. So now you can ask me that sir, in this particular example, actually this is for this particular example, we found out that this result vector was one of the columns of the matrix A minus 2I matrix. This result vector, or this lower eigenvector V11 was one of the columns of this matrix. V12 was also one of the columns of this matrix. So finding out the V21 and V22 was very easy. It was directly you can see and find out. But it might not be so for all cases, right? It might not be so for all cases. For that, how to solve for this ABCD? How to solve for this ABCD? So that I would show you in another example. In that example, I will show you how to find out this ABCD using the column operation method. So in case you are unable to figure out directly, you can go through the column operation method also in order to find out what ABCD would be. So I would do that in another example. So now you see that you have found out your V11, V21 pair and V12 and V22 pair. So your modal matrix M would be simply writing down V11. So there V11, V21 and then V21, then V12, V22. What is V11? 0, 1, 0, 0. V21 is 0, 0, 1, 0. V12 is 0, 0, 0, 1, and V22 is 1, 0, 0, 0. So this is the modal matrix that you have found out. Now, what is your J? J is also simple. There are two Jordan blocks, each of size 2. So these are the Jordan blocks. Again, the same Jordan block. Rest places filled with 0. Check that AM would be equals to MJ. This check you can do yourself. Okay, I will not do the check for you. This is simple matrix multiplication. You will find out that AM would be equals to MJ. Okay. So we move ahead to the next example. So for the next example, let us use the color blue, and let us see the example. So yes, in this example we have a 5 cross 5 matrix. Let us take this 5 cross 5 matrix, which is this A equals to, this is example 2. Okay, so there is a big line here. 2 0 1 0 0 3 minus 1 minus 3 0 3 1 0 1 0 1 3 0 1 minus 1 0 1 0 minus 2 0 3. Let me just do a cross check here if I have noted down correctly. Yes, here the eigenvalues are given. Okay, the eigenvalues lambda 1, you're already told that ma lambda lambda 1 is 2 and ma lambda 1 is 3, lambda 2 is minus 1 and ma lambda 2 is 2. What does this mean? There are two eigenvalues lambda 1 and lambda 2, which are 2 and minus 1. 2 has a repetition of 3 and minus 1 has a repetition of 2. That means the characteristic polynomial is basically x minus 2 cube x plus 1 square. That is the characteristic polynomial. So when you know this information, what you have to find out? You have to find out a minus lambda I. That is the first step. A minus 2i, that is what you find out first. When you do a minus 2i, you will see that this becomes 0 1 0 0 3 minus 3 minus 3 3 1 0 minus 1 0 1 3 0 1 minus 3 0 1 0 minus 2 0 1. Also you have to find out a plus I, a minus I, right? A plus I, which would be, find out that this is 3 0 1 0 0 3 0 minus 3 0 3 1 0 2 0 1 3 0 1 0 0 1 0 minus 2 0 4. These are your a minus 2i and a plus I. Okay, so we have to start with one of these eigenvalues and figure out the eigenvectors. So let us start with a minus 2i. Starting with a minus 2i, you have to find out the eigenvectors, right? So it is not very evident by looking here, looking at this, what would be the eigenvectors of a minus 2i. So we have to do the column operation, and I will quickly do the column operation here. So I will choose this as the first pivot, and if I choose this as the first pivot, I will get this. So I am not explaining the steps here because by now you know how to do column operations. I am simply copying down from my notes. Second pivot I have chosen is here. You should mark your pivots, okay? Otherwise there is no way for the examiner or the other person to know how you have gone ahead with the column operation. If you are not marking the pivots, so you cannot be awarded any marks in the examination. So here your operation ends, because you can see that you have got 1 0 column, and you can very clearly see. So you could have taken other pivots actually, but you can very clearly see that there is no way you can make this, you can combine these 4 columns and result into a 0 column. There is no other ways in which like these two are dependent, or these two are dependent, or like this. So this is obvious from looking at these elements and the distribution of zeros basically. So you can stop here and you can declare, but you should be careful when you are looking at the non-zero columns. You should be very confident that you can stop here. If you are not confident, you can go ahead and do the column operation. Go ahead and proceed with the column operation until you exhaust all the possible pivot elements. So if you are not confident whether these 4 elements are dependent or independent, these 4 vectors, please go ahead and complete the column operation exercise, because you should find out the correct answer, okay? Not rely on your confidence so much, it might sometimes be wrong. But if you can actually see that these remaining vectors are independent, then you can stop your operation here and declare that I have already found out one relationship between these vectors, which is this. So this is my basis vector of the null space of a minus 2I. So I get my v1. v1 I get. v1 is 1 0 minus 1 0 1. From this information that I get is mg lambda 1, which is lambda 1 is basically 2, this is 1. That means only one Jordan block is there, and this means that the size of the Jordan block is equals to 3, because the algebraic multiplicity is 3. Size of the Jordan block is also 3. So there is only one Jordan block which falls into the category of equal size Jordan blocks actually, okay? Because there are no 2 Jordan blocks, so there is no question of unequal sizes. So it is one Jordan block of size 3. So we can proceed with the algorithm 1 to find out the higher order eigenvectors now. from starting from this lower order eigenvector v1. So what to do? My question is now basically to find out this a minus 2i v2. Okay, so v2 to get this v1. So what is this v2 which will give me this v1? Okay, so for that a minus 2i is already here written. This matrix is a minus 2i into some v2 gives me this matrix. Okay, now I am sure that some of you, if you look closely, can very well identify what v2 would be, but let me do the column operation in order to find out what is v2. Okay, let me do the column operation, and this is actually a general methodology to find out the solution to a set of algebraic to a set of these linear equations. Okay, so this is basically a set of linear equation with unknown as v2 and known as v1. So in general we are actually trying to solve ax equals to b form, where a and b are given, x is to be found. So in that case we will actually, what we'll do, we will write down the columns of a and append with the column of b. So we will write down the columns of a, which is the matrix a minus 2i here, and then append with the column of b, which is v1 here. And now we have 6 vectors at the top, so there would be a 6 cross 6 identity matrix at the bottom. Now we again start with the column operation. So again I am taking this as the pivot element number 1. If you are judicious in taking the pivot elements, you will not land into so much trouble actually. That wisdom comes with practice. 0. So let me simply copy down why I am again doing it here. So yeah, 3. So you can observe that we are actually repeating the entire thing, because this will anyway happen, as these first 5 columns are already same. The operation repeats. Now you can choose this as your pivot element. sorry, here I had done a mistake actually. So this would be -3 and -3, and this I hope is okay. Minus, minus, yeah, 0, 1. So now you see that there are two columns, two zero columns, and this zero column we already had discovered before, because this is quite the same as this column becoming 0, and one more thing, these elements are not properly placed. Yeah, so now I am fine. So these are some mistakes I have done in my copy actually. So this doesn't affect the result. So the result is actually to be seen from this column, because this column we already had noted that since these five columns are having some dependency relationship that is coming through this column. But what we need to find out is now what is V2. What is V2? Okay. So what is V2 will be given from this column. How to read this column? You see, what was this column to begin with? This was the V1, which is B actually. These are the columns of A, these are the columns of A, and this is the column of B. So you can read it like this. You notice that this particular column which had the entry for B, that particular column should be 0, so that you have a relationship which tells you that the columns of A are multiplied by which elements, so that you get the column B. So it is like this. So if you read through this line, it is telling you that suppose these are like these entries are like x1, x2, x3, x4, x5, and this is the entry B, right? Because this is 1. It may be something else, should not come actually. It was mostly remain 1. So now your reading is like this. Your reading is that if A is composed of the column vectors C1, C2, C3, C4, C5, then the solution of Ax equals to B. So this actually tells you that x1 times c1 plus x2 times c2 plus x3 times c3, x4 times c4, x5 times c5 equals to your B. And this is exactly what you wanted to find out from this relationship. You wanted to find out these x1, x2, x3, x4, x5. These are what you find out. These are the entries of x. So you have found out. These are the entries of x. You have found out these. Okay. So what is your x? Your x is 1 0 0 0 0 0. So in our purview, we have found out the v2. V2 we have found. V2. V2 we have found out as 1 0 0 0 0. Yeah. Do not include the last one. Okay. This is V2. Now some of you may have already noted that, okay, I think I have done a mistake here. When you subtract, okay, you are not getting this. These entries are wrong. So I have copied down from my rough copy incorrectly. That is the problem. This is what you will get. So your V2 would be 0 0 minus 1. This would be your 0 0, actually 1. Actually 0 0 1 1, because this is actually saying that x1 c1 plus x2 c2 plus x3 c3 plus x4 c4 plus x5 c5 plus b equals to 0. This is what it is saying, this line is saying. So if these are x1 x2 x3 x4 x5 and this is 1, then it is saying that x1 c1 plus x2 c2 plus x3 c3 like this plus b is equals to 0. So b is what? B is minus of these things, okay, minus of this entire thing. So whatever value you are seeing here, you have to take a minus of it, and that would be your x. That would be the entries of your unknown x, which in our case is v2. So you have to take the minus. Please understand this part. You have to take the minus of these x1 x2 x3 x4 x5, so that you can form this vector, unknown vector x. Okay, so you have to take the minus of these elements which you see here. So you have to take the minus of these elements which you see here. So when we do that, we find out that my v2 would be this. Now some of you could already have noticed this, that my v1 was basically the third column of a minus 2i, right? You might have already noticed this. So you could have readily suggested that v2 would be 0 0 1 0 0, because that replicates the third column only, other columns you are making them 0. That is true. You could have simply seen here and directly written that v2 equals to 0 0 1 0 0. But in this case, I wanted to show you the actually the general way of finding out the unknown vector v2, because not always you will have this sort of very good relationship. Okay, though in the example that I have chosen, in the first example as well as this one, incidentally it came out to be in a very beautiful relationship, and you could very easily figure out this v1 was a one vector of the matrix A minus 2i. So you could have very easily figured out what v2 is. Okay, but I wanted to do this exercise in order to make you understand how to actually solve when you have a ax equals to b sort of a problem, how to use the column operation to solve that problem also. And in general, if your v1 is not one of the columns of a minus 2i, then you have to do this exercise and find out what v2 is. Remember one thing, that you have to take the negative of these elements, or in general you read it in this way, that x1, this is x1 into this vector c1 plus x2 into this vector plus x3 into this vector plus x4 into this vector plus x5 into this vector plus whatever is there at the last. Mostly it will be 1, because you have not changed this vector actually. Mostly this will be 1. So whatever is there, that times this vector, the last vector, is giving you 0. From there you have to identify what would be your unknown x. Okay, from that you have to identify what would be your unknown x. So here we saw that these elements need to be multiplied by minus 1 in order to get my unknown v2. in this case. So V2 comes out like this. Now from looking at V2, actually you can very easily see, again you look at the matrix A minus 2i, you see that V2 is basically the first column of the matrix A minus 2i. So if you conjure up a relationship like this, A minus 2i V3 equals to V2, then it automatically gives you V3 as first column, so only the first element is 1, others are 0. This as V3. Again, this in this example, incidentally, it was very obvious, but if V2 were something else, which were not directly the columns of the matrix A minus 2i, then you have to do another set of column operations in order to find out what is V3. So remember these column operations. But here we could find out V1, V2, V3. So all the three vectors, all the three generalized eigenvectors are found out for A minus for the eigenvalue of 2, and we don't have any further vectors to calculate because the size of the Jordan block is 3 only. We don't have any other vectors we need to find out. We don't need to find out V4. So we stop here. We have found out all the eigenvectors we needed, but that is for A minus 2i. Another eigenvalue is with us, which is minus 1, so we have to do the exercise for A plus I. What was A plus I? Let me write down. A plus I was this. This was A plus I. We have to do the column operations in order to find out the eigenvectors, and that would also reveal you the size of the Jordan blocks, because this is also giving me the geometric multiplicity of the eigenvalue minus 1. So a bit long, so I choose this as my first pivot, then I get these, next pivot that I choose is this one. I hope you know the rule of choosing pivot. So wherever you have chosen a pivot, that particular row and column you cannot touch again. So that is the rule for choosing pivots. You see, since I am working with a bit complicated numbers, I am not trying to make all the columns to be 0, because it was very clear that I will not be able to make this column 0. with this. Okay, so I left it actually. This sort of judicious decisions you can take if you are smart enough already in doing the column operations, but you are not having so much confidence, then don't go into this sort of things. You may actually be losing some information if you are not doing it completely. So you can do it, but do it with caution. Do these things with caution. So I am showing this to make you just have an idea that this could be done, but this has to be done only when you are confident that you are doing things correctly, that you are not losing any information because of this what you have done. Okay, now the next pivot I will choose is this, and I will not do any change in the first three columns because I can already see that there is no point in doing any change in the first three columns because I will never be able to make any one of these 0. So you see I get two columns 0. That means my geometric multiplicity of -1 is 2, and I also get the basis vectors. The basis vectors being these, which are W11, let me write, -1 0 0 1 0, and the other one is W12 1 -1 -1 0 1. What was the algebraic multiplicity? Was 2. Geometric multiplicity is also 2. That means I have two Jordan blocks of size 1, which means basically it is completely diagonalizable, and these are the basis vectors, and I don't need to go on to find out the higher order basis vectors. I don't need to do that. Okay, I don't need to do that. So I have already found out all the set of basis vectors v1, v2, v3, then w11, w12, and hence I can write down the modal matrix M as simply v1, v2, v3, w11, w12, and this is 1 0 minus 1 0 1 0 0 1 0 0 1 0 0 0 0 minus 1 0 0 1 0 1 minus 1 minus 1 0 1, and you can do this check that am equals to mj. What is j? J you have to also specify. J you have specified as per the eigenvectors that you have put. You have put the eigenvectors of 2 first and then -1 and -1, and the eigenblock of 2 was of size 3, right? Size 3. Then you have a eigenblock of size 1 which is -1, another again of size -1, size 1. So this is what you get. In the other places you can fill with 0 now. This is your Jordan block. So you can do this check am equals to mj and verify that what you have found out is correct. One thing you notice just before leaving this problem, just notice that what you needed to have, that V3 comes from a eigenspace which is not in the V3 is not in the lower order eigenspaces. So if you compose any vector with V1 and V2, you will not be able to find V3. Verify that. It is very easy to see that with V1 and V2, whatever combination you take, you will never be able to obtain V3. Similarly, V2 is not in the space spanned by V1. So this is true even for the other example. So there was another example that was actually very less number of eigenvectors, only 2. But even in this case, I'm sure you were able to see that your V21 was coming from a space not spanned by V11. V22 is coming from a space not spanned by V12. So this is important observation, and this has to be this forms a very important piece of information when we are dealing with the algorithm 2. Okay. And I think that I will stop here. This particular lecture I will stop here, where we have discussed the algorithm 1 in details. Also we have given you uh, the idea of how to find out uh, the solution of x when ax equals to b. In this form we have written down. So we have to simply append the columns of A with B and find out at the end. You will get the elements of X, and you have to take a negative sign because the relationship is as I had told you, that C1 into this plus C2 into this plus C3 into this, etc., etc., plus B equals to 0. So since it was plus B equals to 0, that's why all these becomes negative when you are putting in X. Okay, that's how you figure out the higher order eigenvectors V2, V3, all these things you can figure out in case your V1, etc., are not very directly related to the columns. So you cannot see the relationship. In case you can see the relationship, you don't need to go through all these things. You can simply say that since V1 is the third vector of third column of A minus 2i, so V2 would be this. Since V2 is the first column of A minus 2i, so V3 would be this. That is fine. Okay, but in case in a particular example this does not happen in this way, then you have to go through this exercise and find out your higher order eigenvectors. Remember, the algorithm 1 can only be applied if you have only a single Jordan block or Jordan blocks of equal sizes. So these two example takes care of both this sort of situation. In the next set of examples, we will see how algorithm 2 has to be worked out when we have unequal size Jordan blocks, and we have to start from the highest order eigenvector actually. So I will leave it here, and in the next lecture I will cover the algorithm 2. Thank you for your attention.